ADViCE webinar on net zero manufacturing and navigating AI for efficiency. My name is David Pugh, and I'm the Director for Sustainable Industries at Digital Capital, and I will be your chair for this afternoon's session. Few housekeeping rules. We are with you on Zoom today. So as you can see at the bottom, there is a Q&A button, which you can use for getting in touch with myself and the presenters and talking through and asking questions. Could we jump to the next slide, please? So today, our agenda is on the screen now. So I'll be kicking things off with just a brief introduction to ADViCE and kind of setting the scene for what we'll be talking about today. And then we've got three really interesting speakers, Craig, Kit, and Alexandra, who will be talking to you about how they're using data and how they are building solutions that are supporting the net zero transition. And then we'll finish with a panel discussion at the end and some closing notes. We won't pause for questions after each speaker, but if you do have a question, please use the Q&A button at the bottom of your screen there, and we will come to questions at the end for as part of our panel. If you do have a question specifically for one person, please do label that as well, and we'll make sure that the right person gets the right question. If we can't answer today, we will pass these all on, and they'll be able to get in touch, and we can address those after the webinar. So if we jump through to the next slides, I'm just going to briefly introduce ADViCE. There we go. So ADViCE is the AI for Decarbonisation Virtual Centre of Excellence. And we exist to accelerate the development of innovative AI technologies for decarbonisation applications and to support the transition to net zero. And the reason that ADViCE exists is to bring together a whole ecosystem of people, companies, and universities and regulators that are involved in this transition, involved in utilising AI and data-driven technologies to support, promote, and coordinate successful adoption. Now, this program is delivered by the Digital Catapult, the Energy Systems Catapult, and the Alan Turing Institute. When we talk about AI, we're looking at kind of three categories of AI applications. So common applications of AI with very little decarbonisation impact. You might see things, very small changes that things can be made, small automations. Applications of AI with a direct decarbonisation impact, and then applications of AI that are targeted at less obvious systematic blockers to decarbonisation. So things we might not think about normally actually play a key role. And one of the things that ADViCE has done is really identify 7 grand challenges for decarbonisation and how AI can really play a crucial role in accelerating the UK's transition to net zero. They're on the screen there. So we have unlocking domestic decarbonisation, enabling net zero infrastructure, specifically energy infrastructure, maximising flexibility in our energy networks, decarbonising manufacturing inputs and improving manufacturing process efficiency, which is where we'll focus today, optimising soil management and minimising methane emissions. And if you'd like more information on any of those, you can scan the QR code on your screen now, and you'll get a virtual set of challenge cards that go into a lot more detail on how each of these challenges can be addressed by artificial intelligence and by practical applications of data. So today we are talking about manufacturing and AI in manufacturing specifically. So we know that about 40% of global CO2 emissions come from the manufacturing sector. And that's primarily due to a reliance on carbon-intensive fuels and raw materials. And so actually, if we want to decarbonize manufacturing, it requires a whole system approach, not just in our kind of foundation industries where we are at the early stage of our manufacturing supply chain, but all the way through to adoption, use, and end of life. And you can see on the screen here, we've got kind of a breakdown of where those emissions lie within the manufacturing sectors. You'll see there's a huge piece there in process industries. And what we can see really is there's a huge opportunity here. If 40% of our emissions come from manufacturing, if we can work on decarbonizing that sector, there is a huge amount that can be delivered here. And so without further ado, I'm going to hand over to Craig to talk about digitalization approaches for manufacturing.
Thanks, David. So I'm Craig Douglas. I'm the CEO at Dataflow IQ. We do digitization specifically in manufacturing. My background is both IT and manufacturing. So I've been in manufacturing for around 15 years, and I've been in IT for over 20 years, of which 8 to 10 years of that has been more at a strategic level. So that has been looking at overall data strategies, how we can integrate different systems, gain visibility on different platforms, and so on. And that's what we focus on now at Dataflow IQ. I don't seem to be able to, there we go. So why digitize? I think the reason why many people buy things or solutions are either because they're forced to, due to regulatory reasons, to increase profitability, either increasing the top line or improving the bottom line. The final reason is to prepare for AI. AI is only as good as the data that it's working on. AI gives us a huge amount of power to automatically process large volumes of data. If that data is incorrect, then the output is going to be incorrect or untrustworthy. Practical uses for AI in manufacturing as examples, things like predictive maintenance. Reducing downtime of machines is a significant cost saver for manufacturers, but it's also a sustainability improver as well. Any downtime in one machine that then has knock-on impact to other areas, all of that time spent is wasted resources in terms of manpower, but also wasted resources in terms of running the facility. Production scheduling and balancing, the better utilization of machines and resources that you've got within your business will help improve sustainability. Quality control, time and motion capture and analysis, and health and safety are other use cases in manufacturing. We're not doing anything with health and safety, but we've got active projects on the first 4 of those points. So where do you start? Where do you start to digitize? And starting digitization, even if you're not getting to AI yet, just starting that journey of digitization will deliver huge benefits, and then you can gain greater benefits later on with AI. So you can start small, looking to reduce downtime. You can start by tracking machine usage, downtime reasons, so understanding the root cause of why your machines are down for periods of time, and understanding the Pareto of those. So what is the most common factors leading to downtime? Tracking power and vibration data can lead to predictive maintenance. Increased productivity. Tracking manual processes. Manual processes within manufacturing is a huge area of opportunity to reduce resource usage and therefore improve sustainability. It's a difficult problem to solve when you've got manual production. So we work with modular home manufacturers and so on, and furniture assembly. With that comes a lot of manpower and a lot of offline processes that are less easy to track. Introducing things like MES technology has got a huge potential to understand where processes are slower than they could be or should be, and understand the reasons behind those. Tracking performance, live feedback and visibility is a huge area. If you have got particular targets for particular teams, but they can't see how they are progressing towards those targets, it becomes a challenge, and it almost becomes a bit hostile, because you're telling people they haven't achieved their targets after the fact. Whereas if they can see what they're doing, whether they're ahead or behind, that leads to a huge performance improvement. Transact materials in real time. This might not be particularly obvious, but a large proportion of time wasted is in waiting for materials or materials running out on the shop floor. If you're able to transact operations and consume the materials in real time, that will lead to more efficient processes within the facility. Now, ERPs are designed to do this, but ERPs don't always lend themselves well to user operability on the shop floor. And that's where something like an MES can come in as the interface for the shop floor operatives to then transact in the ERP platform. And then optimizing energy usage, real-time energy monitoring, machine and labor utilization. I've kind of already covered a little bit, but it's just to underline that we're doing a sustainability accelerator with Digital Catapult. with a concrete manufacturer, and they have beds where they are making walls, basically, where they've got molds, they pour concrete in, and the concrete needs to dry for a period of time. To improve the speed at which these walls are made, they're heating these beds all of the time. They've got 14 beds in a facility, and they haven't got high utilization of these beds. So by starting to track and understand the utilization of these beds, they can then turn off the heating of some of these beds and plan their production processes better, saving a huge amount of money, but also reducing the amount of labor and potentially increasing productivity as well, because you're not spread out across so many different areas of the facility. Moving on to the next slide. That is, so this was a case study at Ilke Homes. So they were a modular home manufacturer, and they had the scenario that I just described, really, where they've got a lot of manpower on the factory floor. They had poor material replenishment processes, and they had poor visibility of what was going on in the factory. By introducing a very lightweight MES solution to transact in the ERP, so it was just point and click of completing tasks, they were able to increase their productivity by 20%. Now, some of these challenges, some of the ways to digitize span a few different areas. Now, there's the practical and physical side of things, which are things like sensors. So simple power monitors to monitor machines can be done in a non-intrusive way. So you're not having to interrupt the operation of the machine. You're putting a CT clamp around the power, or you're using existing sensors that machine has got and daisy chain those inputs to a collector device to be able to push all of that data into an analysis platform. You can integrate directly with a machine. Doing this is more intensive and will be more costly, but you will get a lot more information from the machine. So more accurate data of fault codes from the machine, for example, so that you can understand when things are happening, what things are happening as they are happening. And as I mentioned, you've got the low-level PLC, then you've got the high-level ERP, which is more for planning and some operations, and then the MES is really the area that a lot of people miss, but that is the actual live activity platform, not the control of the machines, which the PLC does, but the live activity. And getting the data from there gives you a much richer set of data than the ERP high-level data, and will start to give you the feedback of what the reasons are for things being delayed, or the fine detail of where delays are happening, which then gives you that feedback to be able to conduct a continuous improvement approach. With all of this, well, not all of this, with the sensors, you don't need to, it's not so much of a big culture change as it would be with an MES solution, for example, and the people side of things are a huge factor as to whether or not a digitization project would be a success. Getting their buy-in early and including them early in the process, and getting them understanding the benefits and how this is going to help them, will lead to better adoption. And that really depends on how well this is delivered through training and through leadership as well. And another key area is to make sure you've got a very simple visual concept as to what your data strategy looks like. So what data are we collecting, how frequently, what level of detail that data is being collected, where that flows through, and how you're going to gain insights from that. So common barriers to digitization are things like high initial costs, complexity of integration. I mentioned integrating with machines directly is a bit of a challenge, but it does give you much greater level of detail, and resistance to change is a little bit more on the people factor side. mitigating approaches. Start small. You could start by just introducing a sensor on one machine, a simple tablet to capture the reason for any downtime. And you can use scalable cloud platforms to be able to interpret that data or provide the operator feedback to say what the reason for that downtime was as it was happening, and then you can start to trend that over time. Benefits. Okay, we've talked about it's a precursor for AI. However, you can then get a lot of other benefits just from the digitization steps that we've talked about. So you can start to be alerted on any downtime. So that could alert your maintenance team, or it could alert production leads. Energy issues is another one. You might get we've seen voltage spikes on the power supplies to facilities, which can then lead to motor issues or affect components on your machinery. And tracking things like energy consumption over time. If the same machine is building the same widgets over time, energy consumption is going up and up and up, there's probably a good chance that that machine needs some maintenance. And then continuous improvement, being able to gain the not just knowing how much downtime you have or what your OEE is, for example, but understanding the reasons behind that is a huge driver towards being able to reduce your downtime or increase your productivity. And this will give you a direct contribution to reducing emissions. We talked about machine utilization. If you can increase your machine utilization, you might not need to add another machine, or you might be able to turn off particular machines. And the real-time visibility of all operations is another great benefit to all of this digitization. As an example, live maps of your factory to see machines, their overall OEE, easily identify which particular machines have had challenges today. Now, that could be for a variety of reasons. It might be tooling changeover, where you actually need to plan production better so that you're not changing your tooling so much. It could be maintenance. It could be lack of materials. It could be shortage of orders. So there's a wide variety of reasons, which some of them will be maintenance driven, some of them will be planning driven, and some of them will be more operational. Again, this is the example that I just talked about with the project, the Digital Catapult and Sustainability Accelerator, being able to get a real-time view of what's happening in a particular factory from another location. So this particular factory, with all of these beds making these concrete walls, there are other parts of the facility that are making the components for the next orders that are going in, and there's other areas of the facility, like the finishing areas, that are waiting for these walls to come through. So being able to give them visibility of what's happening in a geographically spread out facility leads to further efficiencies as well. And yeah, more examples of live wallboards. And yeah, I guess the bottom line from me is that digitization is not just a step forward, it's more of a leap towards sustainability, and sustainability as well from a practical point of view for manufacturers almost always leads to profitability as well. So that's everything from me, and I hope I've not gone over time.
Thanks, Craig. That was great. Our next speaker is Kit Winders-Yule, who will be talking to us around using numerical simulation and evolutionary optimization to improve efficiency of industrial processes. Kit, you have the floor.
Yes, indeed. Thanks, David, for saying the title for me, because it is a little bit of a mouthful. So my talk actually complements Craig's rather well, because Craig has sort of talked about all the ways you can improve efficiency in your factory under the assumption that your actual machinery and materials are behaving well. So my talk is more about if the equipment you're using itself is inefficient, and trying to improve efficiencies in how you use and design industrial equipment. So first, a little bit of background, both about what I'm talking about today and about myself. So I wear a variety of hats. I'm the founder and CEO of a startup called ADViCE, and that gives me a lot of experience designing and applying AI tools in a diverse range of industries. I'm also an independent scientific advisor for the Innovate UK Bridge AI scheme, which means I get paid for 1 day a week to go and travel around the country and talk to lots of different SMEs about how they can better adopt AI and benefit from AI tools. I'm also an industry fellow, which allows me to be seconded part-time into the local company who are producing uh, biodegradable, bio-derived and recyclable plastic. So sustainability all over the place there. And that's given me experience of applying AI from the inside of a company. I'm also the Director of Innovation for the College of Engineering and Physical Sciences at the University of Birmingham. That's a role that allows me to work with a lot of companies from the startup to the SME to the multinational, and has a heavy AI and sustainability focus as well. And I'm also a research ethics reviewer for the Alan Turing Institute, which is a very important role because it means that not only do I think about how effective AI are, I also think deeply about applying them in a way that is safe, ethical, and sustainable, which is an area that can often, all too often, be overlooked. I'm speaking you with my ADViCE hat on, I should mention. So one of the reasons I co-founded this company was this fantastic quote from the seminal Merrow report produced in 1986, which is effectively saying that the design of process equipment in the solids handling sectors, and also various others besides, is simply not getting better. Okay, and he did a follow-up report in 2000 and found that things are still not getting better, and another follow-up report in 2022 and found that, shockingly, things are still not getting better. There is a real efficiency problem in the manufacturing industries. So his conclusion, to sort of paraphrase it a little bit, is conventional research and design processes are not fit for purpose in a lot of different industrial sectors. They're too slow, they're too expensive, and there's simply too high a risk of failure. So we founded our company to find a new way of addressing these issues. So our solution, as we see it, is firstly to use numerical simulation to replace physical trials and the construction of physical experiments with very robust simulations, reducing the time aspect, the manpower aspect, and the cost. To replace manual design with AI-informed programmatic CAD, so actually redesigning both the systems themselves, but also the way that they are operated, so the processing parameters using programmatic AI-informed design, and to replace conventional design of experiments, again, with artificial intelligence. So instead of just conventional design of experiments or trial and error, you can use artificial intelligence to explore these parameter spaces, these design spaces, in an intelligent manner. So that's all a lot of very nice buzzwords. Sometimes it's useful to see what an example of this actually looks like. So this is a nice visual case study. And one thing that's important to say outright here is I like to use this case study because it's visual, it's pretty, and seeing the evolving geometries of these systems can be very valuable. But the same kind of concepts and ideas and technologies can also be applied to much simpler problems. For instance, changing the operating parameters, so the rotational rate of a blade, the feed rate of material into a system, etc., etc. So this is just one case study, but it can be applied to a much broader range of systems and ways of optimizing your system. So this particular case study was some work with Unilever, so a very, very large company who work in the fast-moving consumer goods sector, and they came to us with this mixer. Okay, so we're trying to, hypothetically in this simulation model, we're trying to mix this red fluid in here with the rest of this container. And as you can tell, it is not performing very well. So our job was to try and improve the efficiency of their design. So the goal was to improve the mixing efficiency without increasing the power draw of their system. And this means they get increased throughput, so they get the profitability, as Craig was talking about, but it also means reduced energy use. If I can mix this thing twice as fast with the same input energy, then I'm using half the energy to produce the same amount of product. So that's a very powerful thing to do if we can do it. So what we do, the way our software works, is we ask for an objective function. So in this case, what Unilever wanted was to increase the rate of mixing. So we defined what we call the tracer uniformity index. We found the exponential function that describes its increase with time. And our goal is basically to minimize this parameter here. I won't go into the mathematics, that's not what we're interested in here. But the point is, we have this t-half parameter here, and we want the smaller we make this, the faster our mixing is. So that becomes the objective function, the fitness function, as we call it, of our optimization problem. So the basis of the technology we use is evolutionary optimization. For those of you who don't know how evolutionary optimization works, it's actually conceptually extremely simple. It works like normal Darwinian evolution. So to provide a sort of a more Darwinian example, let's imagine we start with an initial population of some animal, let's say a bunch of birds. These birds, this population, this family of birds, they all have a different degree of fitness. So if we're talking about real live animals, the fitness of these birds might be how well they can fly, for example. Now, the ones that don't fly very well, they're going to get eaten by predators, they're going to fly into the sides of buildings, they're otherwise going to be removed from the gene pool. The ones that are very fit, that fly extremely well, they're going to live long and prosper, and they're going to pass on their genes to another population of birds. Now, obviously, at ADViCE, we don't care about birds. That's not what I'm interested in. I'm interested in industrial mixers. So what we do instead is we create a generation of, say, 100 different mixer designs, all with completely different geometries and/or operating conditions. Okay. We then assess the fitness, so how well does each of these designs mix, and then we kill off the ones that don't mix very well, and we breed, as it were, the ones that do mix very well. And we can vary all sorts of parameters. So with these programmatic CAD models, we can change how many plows we have on our plowshare mixer. We can change the angle between them. We can sort of open them up like flowers. We can twist them. We can make them taller. We can make them longer. And what this allows our AI to do is to actually, if the slide wants to show that is, there we go, is produce all of these completely unique designs that probably a lot of these may well not come out of the human mind. That's the power of using these optimization strategies. And this is what it looks like as it evolves. So this is the best. We run generation after generation after generation of these simulations. And if you look at this graphic, each one of these dots represents an entire design for our system, an entire simulation. The original design is somewhere down here, so you can see that from the very off, our AI is coming up with much better designs because the rate of mixing is going up exponentially. And we find it eventually converges to an optimal design. And the thing to bear in mind here is we have here roughly 2,000 different designs, okay? And it designed and tested each of these, all of these, within 8 days. Imagine trying to do that through conventional manufacturing trial and error approaches. Of course, with any of these things, seeing is believing. So on the left here, we have our original design. In the center and on the right, we have our evolved designs. And the difference in the rate of mixing experience between these two systems is, well, as you can see, considerable. Again, we don't just work with fluids. This is an example of some powder mixing. This is with a with a different company who are interested in mixing two different components of foodstuff together. So the original design on top, still struggling to get started. The evolved design on the bottom, pretty much finished already. And of course, things that aren't mixing at all. So we did some wonderful sort of trial work with the company looking at trying to improve the efficiency of their milling systems. And we found that these improved the speed by about 43%. I should say I forgot to quantify the Unilever one. We increased the speed there by a factor of 10. So a 90% energy efficiency saving for that particular design. And of course, the most exciting things we're working on at the moment is tailored wind turbines whose geometries are optimized for the specific wind speeds and urban design of different regions of the UK. So at the moment, we've designed and built one for Birmingham. We're building one for Edinburgh next, and the designs are completely different for the different cities. It's quite striking. So to summarize, the expense, complexity, time-intensive nature, the labor-intensive nature of R&D in industry can be a serious limiting factor in making our manufacturing processes more sustainable and more efficient. But you can overcome these using the intelligent application of both numerical modeling and evolutionary optimization, or indeed other forms of AI. And the workflow demonstrated here is a particular case study with a particular system, a particular set of tools. However, the same kind of approach that I've described can be applied for various different systems, various numerical models, even different kinds of AI-driven optimization. The goal here today was to demonstrate the power of AI in accelerating this R&D process by orders of magnitude and reducing its cost by orders of magnitude as well. So that's all I've got to say. I'll hand back over to David.
Thank you, Kit. That was really interesting. Our final speaker for today is Alexandra Brindler from the University of Cambridge. Alexandra, you have the stage.
All right. So hi, everyone. I'm Alexandra Brindler. I'm the professor of digital manufacturing at the Cambridge University's engineering department. And also I'm a fellow at the Alan Turing Institute. I did the digital manufacturing activity there. So at Cambridge, I lead a lab called the Supply Chain AI Lab. We are a bunch of computer scientists, mathematicians, complex scientists, and supply chain management people who come together to solve supply chain problems using AI and data science. Oops. So what I'll very briefly talk to you about today is kind of state of the nation, I guess, in supply networks, and how we are beginning to enter a new era of data science and supply chains, and what's kind of what can we do that we couldn't do before with supply chain AI. And I'll give a kind of selection of exotic supply chain AI, let's say, where I'll talk to you about traceability, predicting food ingredients, and autonomous decision-making, but I'll also talk to you about efficiency improvement and kind of the more traditional applications of AI for sustainability improvement in supply chains. And then I'll conclude with kind of our need really to enter into an interdisciplinary perspective to be able to make the best use of AI. Okay, so supply networks emerge as companies start buying from one another to produce their own goods, and that creates dependencies between firms, between countries, between modes of operation. And for a long time, we really didn't have data on the structure and function of these sorts of constructs. We don't know how they emerge, how they look like. So because nobody really designs and controls a supply chain, right? So they don't have visibility over their extended supply chain. Firms that are embedded in this complex network, they know who they buy from, but they don't know who those guys are buying from most of the time. So now, in the past decade, we started being able to map some of these structures using a combination of AI and data science and secondary data sets, which I'll talk to you about in a bit. So we now know a lot more. We know that these structures, they tend to be very large. So a typical car contains about 40,000 components. About 80% of them would be outsourced. There would be about up to 40,000 suppliers in an OEM supply chain, and they would be sharing suppliers with other OEMs as well. So now we know that they have, although they emerge, they're far from being random. So they resemble complex systems that we find in ecology and biological systems as well, which is also, good news and also bad news. It's good news because of their stability. So they tend to be stable and robust to random disruptions. It's bad news because if certain types of disruptions happen, those disruptions tend to cascade throughout these systems. Now, a recent study found that Western manufacturers are no longer than 3 degrees of separation away from very contentious issues such as supply chain slavery and also deforestation. So because of the shape of these supply chains, because of the hub-spoke structure of these supply chains, when we in the West are procuring goods from in different industries such as fashion, chocolate, automotive, we are really no further away than about 3 degrees of separation from places where deforestation and supply chain slavery occurs. Okay, so and in response to this systemic issues, really, the Western world is really trying to find solutions, both in terms of new technology, both in terms of reshoring and kind of reconfiguring supply chain structures, improving our security, our resilience, our sustainability, and AI is really one of those tools in the toolkit. So. As I said, we have been trying to really map these structures since about 10 years now, and here are some of those pretty pictures. You see automotive here, automotive industry, fast-moving consumer goods industry, and aerospace industry. They share certain patterns and characteristics that we can really now start to understand how really the structure emerges and how is it generalizable across these systems. And we can now estimate supply chain links and volume of transactions through machine learning, through graph neural networks, crawling through the web, and teaching large language models, for example, how to recognize supply chain relationships. And researchers have even tried tapping into phone conversation data, not conversation, but telecom data to understand, who is talking to whom, what firm is talking to what firm, and VAT data sets. So we can now map. So, for example, this is the entire economy of Hungary, and satellite imagery and even bank transactions, bills of lading data can help kind of map these structures. So what have we learned? We know that there are about 300 million active firms and 13 billion links globally. Immediately tells you, very dense networks here. It's a very small world. So again, we are short, path lengths to different manufacturers are very small. And we have certain patterns that also inform our understanding of how disruptions might cascade. So, oops, sorry. And about 80% of, global flow really passes through multinational corporations. I won't go through the kind of technical details of these because I thought I had a little bit more time, so I'm not kind of introducing you to the maths and technical behind all of this. But really, the point how we can really relate this to sustainability is if there are hub firms and those firms have exponentially larger degree of connections, exponentially larger degree of transactions that occur in this global system, which is what we're finding out, that means those hubs are very, very central to sustainability issues. So the question is, can an improvement in them cascade through to different firms in the network? And another reasonable hypothesis would be that those firms who produce the most products, perform the most transactions, they will be influential in the global system in terms of their sustainability and in terms of influencing other dependent firms for sustainability improvement. So I'll just skip these slides, apologies. And so now, what we have done is using our own kind of AI-based algorithms, which we are able to surveil supply chains with using secondary data, and then teaching algorithms how to kind of guess who supplies to whom. Now we have created this map of the automotive industry, and this is a very smaller subsample in the grand scheme of things. It's about 4,500 companies with 27,000 relationships in them, but there are 7 different major OEMs here. Now we combine this data set with data sets that give us emission scores. And then what we have tried to do was try to predict whether we can actually estimate carbon emission of these companies from their structure, where they are embedded in this global network, and in amongst other variables. So it seems that emissions, they are mostly in tier 1. But then they flatline between tier 2 and beyond. Environmental scores, if they're available in the data, even though they are black box scores, given by companies, and we don't know how they're calculated, their structure, they allow prediction of emissions up to 85%. Actually, though, the topology of the network, it explains quite a bit. So that hypothesis of, the larger you are, the more you emit, the more degree you have, the more central you are to the network, the more we can predict your emissions. It's true. And also, our kind of correlation analysis has suggested that the high-performing companies, they influence their neighbors. So, and we did a diffusion analysis, where we have taken kind of companies with operating revenues of higher than 4 million, and we found out that a 10% improvement of emission scores in those companies, they can yield on average 2% improvement on the extended supply network. So not even on the first tier, but also the tiers that they have no visibility over. Okay, so that's kind of the relationship between structure and carbon emissions. We can also use AI to predict ingredients, so unsustainable ingredients. In this case, we have taken a large data set from 2 supermarkets, and then looked at labels to detect palm oil. Palm oil in the UK is disguised under 250 different names. So it's not actually, if you don't see it on the label, you can't really be sure that it's not in there. So consumers really need a way to find, whether actually palm oil is in there. It is, palm oil, as you might know, it's really responsible for a large amount of unsustainable issues in countries like Malaysia and Indonesia. So and we have been able to kind of teach algorithms using product ingredient data. Even if we don't see it on the label, we are then able to create models where we can actually predict what's in a food product. So I have mentioned also that we can also use AI to remove waste from the network, and that's kind of where efficiency, which is the kind of title of this webinar series, is where traditionally AI is being applied in supply chains to make things more efficient. So one of the ideas that we have here is because of the structure of the network, as I said, it's an exponential hub and spoke structure. What we have found out is that actually, in order to ride out certain types of disruptions, you can minimize your inventory as opposed to other types of topological configurations. So your structure has a really big influence on how much inventory you actually need to carry. So you can then start to reconfigure your supply network based on that knowledge. And here we have used an optimization algorithm similar to my colleague before, evolutionary optimization algorithm to try and achieve that. I will give one more example, and this is kind of, so I started with predictive analysis, moved on to optimization, and I also want to point out automation. So automation is very much the endeavor of AI. It is to create an intelligent agent that kind of mimics a professional, a supply chain professional, in my case, that takes intelligent decisions. Now, this is useful in situations where manual interventions, companies don't have incentives to kind of, or the resources really to take interventions. An example of this is collaborative logistics. So in the UK, we have a high goods vehicle utilization of about 60%. So that means 40% of the time trucks are traveling empty on the roads. An obvious, answer to this could be to increase truck utilization, perhaps by carriers sharing loads that are on the journey. Right, so that would then remove unneeded vehicles from the road, and again, high goods vehicles they constitute about a 5% volume of carbon emissions in the UK. So it's a big problem. So here, companies, so carriers, they don't have really incentives to share trucks. And the reason for that is they don't know who is going where. They have to change their own business processes. They have to change their own routes that increases the distance traveled. And they don't know how much they will gain as a result. If they also outsource this decision to a central mediator, they have to pay for that central mediator, and they wouldn't actually gain anything back until enough other carriers subscribe to this. So it's a typical, game theoretic problem, and we have applied game theoretic AI for this in the form of multi-agent reinforcement learning. And it's a complex problem, right? So we both have agents representing carriers. They need to share trucks. They need to optimize route. They need to optimize, co-optimize the route. They need to co-optimize the truck space. And then also negotiate on a value. So if a company says, listen, I'm taking 90% of the trucks, so I'm gaining 90% of the profits, it won't work because the 10% guy isn't going to agree to it because 10% isn't enough for him or her to kind of change their own business processes. So that's why it's a kind of game theoretic negotiation or consensus seeking problem where we are able to apply AI algorithms to kind of negotiate automatically, first being trained on the users and then kind of apply to the problem to try and enable this. So yeah, we are getting there. It's working in kind of small scale problems, but in order to kind of increase it to the larger scale problem, we still have some way to go. And here we think that new found algorithms, so I talked about multi-agent reinforcement learning, but also LLM agents can also really help. And the advantage of LLM agents is actually then we can actually tap into their conversations and find out what they're doing. So it all becomes much more explainable and interpretable. And the same consensus seeking algorithms and those approaches can be applied to other sustainability problems, of course. So I think I'll just finish maybe just with some concluding thoughts. We have entered into an era of data-driven supply network analysis. And this era is really offering new technical solutions to long-standing challenges, such as consensus seeking, information sharing, visibility. So there are many opportunities for sustainability monitoring beyond just improving efficiency. Okay, so it's not just about optimizing, it's also about consensus seeking, it's about information sharing, improving visibility, finding out who is who in the supply chain, who is responsible for carbon emissions, who is responsible for wrongful deforestation, and so on. But at the same time, we need to be aware of potential pitfalls. These technologies are all new, although there are many companies now that are popping up and saying, yeah, we can do this, it's new. And many times those algorithms they run into issues when it comes to real life problems and scale of challenges. So there is a path ahead, but it's the trajectory is kind of steep. We haven't, I think, reached a certain altitude yet, but the trajectory is getting there. And also kind of operational and governance considerations need to come into play when we do get there. What will we do with this information? Okay, so I'm gonna stop there. That was a very, very fast whistle-stop tour of our research that's related to sustainability. If you want to find out more, please get in touch with me. And this is also researchers from my lab, and a lot of this is their work. Thank you.
Thank you, Alexandra. Can I invite all panelists to rejoin me on the virtual floor? If you have any questions for any of the panelists, please pop them in the Q&A box. We've got a few coming in, which we'll get to briefly. But before we get to those, I'd like to just ask 2 questions more broadly to the panelists. So the first really is that everything we've spoken about today is talked about kind of data availability and quality being crucial for AI-driven decarbonisation. And so what can manufacturers or players in the supply chain do to ensure that they have the right data infrastructure in place? And Craig, I'll come to you first on that one.
Thanks, David. So data is incredibly important, that it's accurate. So capturing that data in the at source and then storing that data. So there's a few different strategies you can take. You could store that data on premise. It's probably the cheapest way initially to get started to store it on premise. However, you then have to manage that data, whether it's database or flat file structure, and then being able to then leverage AI then becomes more problematic. Potentially you can export some of that data and upload it into some AI models. However, if it's large volumes of data, a cloud approach is probably a better approach. The downsides of cloud, well, while cloud allows you to scale significantly, and some more modern solutions can reduce the amount of management that's required, it does also require a bit of knowledge to set up and particularly to secure it as well. So then there are SaaS solutions such as Dataflow IQ, where we can then pull all of that data or ingest that data, store it securely in one central place. You're looking at data from many, many different data sources, and you don't know the kind of use cases that you will be wanting to implement AI or other analysis tools on this data, which data you'll need. Being able to collect that and store that all in one central location will then enable all of those future analysis and use cases.
Yeah, that's great. And Kit, does the same rules apply to the optimization challenges you're facing?
Yeah, so I'm going to take off my EvoPhase hat a second and put on my University of Birmingham hat, because I don't want to just talk about sort of the very specific things we do with EvoPhase. I want to talk more generally about AI. And I'm going to come at this question from an ever so slightly oblique angle and sort of say, from working with a lot of companies of a lot of different sizes, I'm acutely aware that it is simply not possible for everybody to collect high quality data and collect large amounts of data, especially if they don't have that data today. If you want to train a neural net, or if you want to train a large language model, you're going to have to be collecting data for several years before you can even do that. So what I would recommend for companies who are in that position is there are ways of working that don't require that vast pool of historic high quality data, which simply isn't possible for all of us. So for instance, so the example I gave you with the evolutionary optimization, one of the strengths of that is it's not a data-driven model. The data are all created by and then used by the AI itself. All you need is one starting digital model or tools you want to optimize. So that's one way of doing it. But also beyond just that, looking at methods, looking at AI models that don't require large amounts of data. So for instance, in my work with companies like AstraZeneca, GSK, also Unilever, we make a lot of use of machine learning tools like symbolic regression, because with using these tools, you can actually use, we've had great success. We've published a couple of papers with AZ and GSK with as few as 32 data sets. 32 data sets, compare that to the tens of thousands that you use if you wanted to train an artificial neural network. So sometimes using the data hungry, sort of the big deal, the really cool latest thing like large language models and transformers is very appetizing, it's very appealing. But if you step back a couple of decades and use something more like symbolic regression or random forest, you can do a hell of a lot more with a much more limited data set. So my advice is don't think too much about having to have a vast amount of data. Choose your tools and methods wisely, and you can get away with limited data, or you can get away with no data.
And Alexandra, how have you found working not just across one company for data, but actually a whole supply chain of different organizations?
It's so when we started, right, there was no data on supply chains. So the pretty pictures I showed at the very beginning, it was kind of hand collected. So it was very, very hard. So we literally went to Japan and also validated, using translators and so on, which then motivated us to kind of find solutions to automatically map supply chains. Then we tapped into, World Wide Web, and various other databases too. So I think the key difference in my field is that firms aren't willing to share data. So you take two perspectives, right? So you either find data and become very creative, both with your algorithms and what you can, where you can find data, which let us to do telecoms. If you're speaking to another firm more than 9 minutes a week, apparently they are your supplier. So that kind of leads us to find interesting patterns as well. But the other viewpoint you can take is to think about being a firm embedded in this ecology, and in that case, then you find data on that they traditionally collect, such as ERP systems and so on. Then you start taking this viewpoint that is kind of, you still are data rich, but you don't know the external system. So we're trying to bring those two things together, which is challenging, but also very interesting.
Absolutely. It's interesting you bring up that companies not wanting to share data. It's something that I think we all face quite often. I'll come to you first. What are the kind of challenges and risks associated with kind of implementing AI, and how can we minimize those risks for adoption?
Yeah, I mean, obviously there are many. The two that I see the most in my various roles are, number one, simply implementing AI badly or implementing the wrong AI. It's really important to have a good grounding in what you want to implement. So effectively, a lot of people implement AI because they just want to implement AI. And that's approaching it from entirely the wrong direction. What you need to ask yourself first is, what is the strategic goal that I want to achieve? And then you need to talk to somebody who actually really knows about this stuff to try and choose the right AI for your purpose. I found a lot of times with companies I've worked with, is actually sometimes you just don't need AI at all. The second risk is the ethical risk. And I know this is all about AI for sustainability, but just because something is sustainable doesn't necessarily mean that it's ethical. And one of the big things that companies should really think about when they're bringing this in is the human impact, things like workforce displacement, workforce alienation. If you're improving efficiency, are you improving it in a way that just lowers energy bills, or are you improving it in a way that removes jobs? And in terms of minimizing the risk, the real advice I could take, other than taking that step back and looking at it strategically, choosing the right AI, is the old adage of measure twice, cut once. Look at all the ethical risks, the safety risks, the security risks before the project starts. And once the project has started and you've developed this AI tool, take your time to rigorously test it and validate it, fully understand the model you're working with, make sure that you have tested it at all the edges of the parameter space, the edge cases as the buzzword is, and make sure that there is some form of human oversight at all steps, even when you validated it. So yes, just take a cautious approach, because the money it might cost you not to implement your AI for another 4 weeks is a lot less than it will cost you if you do something disastrously unsafe or unethical and then lose your entire client base.
That's great advice. Alexandra, do you find similar challenges when asking companies to share data? How have you kind of worked with them on the risks of AI?
So I guess two separate questions there. One is, companies sharing data. So companies sharing data with us is not a problem, but companies sharing data with each other is a big problem. Now, and as you know, supply chains are sequential, kind of interdependent. They exhibit these dependencies, and they need to coordinate together to make decisions. Which is where, supply chain wide end-to-end supply chain data becomes crucial. Now, I haven't talked about it in the presentation, but we have been working on something called the privacy preserving information sharing platform. And here, again, a very interesting kind of approach from the field of AI has emerged, which can be used to solve this age-old problem of I don't want to share data with my supplier or my customer, and that has helped quite a lot. So the idea there is, because we have always assumed that we need data from everyone to go into some kind of data lake or some platform, and then we make our prediction models on it, be it demand or risk or whatever. Instead, with this approach, what you can do is you create a common information model, common predictive model, let's say, and in this case, each company they give local updates to the model. They train the model locally using their own data, and then they send parametric information to the global model. Let's say this could be a common demand prediction algorithm for the supply chain, or it could be a risk prediction algorithm or a pricing algorithm or something. And and companies won't want to share data there because if they do, they fear that they will just figure out each other's cost structures and they can bypass them and so on, all sorts of issues. So it worked. I don't know if it will work in all sorts of scenarios, but at least in 3 different case studies, it did work. So there are kind of solutions that from the computer science field that you can throw at this problem. But I am also equally, I think, mindful that there will be cases where it won't work. Technology isn't the solution to everything. So in that case, I think companies, and that's very much like what Kit was saying, they need to know, they need to understand the benefits before they will sign up to that.
Absolutely, it's a great point. And speaking of benefits, Craig, when we talk about manufacturing, we don't often think and talk about people on the shop floor and how they would be using kind of these tools. What can we do to help the kind of workers on the shop floor get ready for AI coming into their organizations?
I think there's many different ways that AI can be introduced on the shop floor. Particularly, I think starting to collect the data. I think Kit mentioned that many manufacturers are not collecting data, and collecting the data is the precursor. You need to understand what is happening now so that you can work out whether or not the outputs from the models are actually going to improve things or not. Then it needs to be able to identify where there are gaps, where there are bottlenecks, whether it's material replenishment, whether it's particular tasks taking longer than expected, for example. So there are, it might be people on a shop floor that have got machinery. Being able to collect data when it's machinery is far easier than if it's manual production. So if you've got machinery, most of that machinery will be powered. So that power can be monitored. You can start to track utilization, drive OEE, being able to start collecting that data, and then potentially start to look at automated quality capture, being able to automatically detect and identify good items from bad items. You can then start to collate other parameters. For example, a particular customer of ours, they manufacture wound dressings, and the quality of those dressings varies depending on the humidity in the room. So by having sensors such as humidity and temperature sensors combined with the automated quality capture, as much data as you can capture automatically as possible will then be able to help feed in all of these parameters into AI models to be able to identify what is the optimum parameters to be able to produce good items. In non-machine manufacturing, so where you've got a workforce, tradespeople, and so on, it takes a little bit more time to start collecting that data. So you need to introduce the simplest form of data capture, and it needs to be done in a way that actually benefits those people, because otherwise there's no reason for them to use it. So in the process of them completing a task, perhaps they need standard operating procedures, work instructions, and so on. Introducing an MES that provides that information to help them do their job better gives them the benefit, but you can also start capturing the data, how long tasks take, who's doing which tasks, the training levels of different people doing particular tasks. All of this data then helps prepare for AI, and then AI can start to schedule what the best utilization of resources is to be able to deliver a more sustainable production facility.
Brilliant, thank you, Craig. And Kit, same question with your many AI hats on. How have you found good ways to help kind of adopters of AI that would be using these tools day to day?
Yeah, absolutely. So I think the first and most fundamental thing would be for a company to try and improve AI literacy amongst everybody in the company. I think a lot of the time when we're talking about the shop floor workers, AI means something different to those in the ivory towers, as it were. So one thing that we try and do when we are implementing AI in a company, and I say we, encompassing both the work I do at the university and with ADViCE, is we take the time to canvass opinions, to talk to the shop floor workers as well as just the executives, to explain the benefits there will be to them, to be open about the negatives that will be for them. And the crucial thing that we have found really powerful is to actually allow the shop floor workers to be involved in the design, development, acquisition process of the software, of the item or the process that they're adopting. So, for instance, one of the really nice examples about this was when we were doing the project designing geographically optimized wind turbines. We actually had the metal workers in the room as well as the CEO of the company. And not only did that make them feel they had ownership, they had sort of some skin in the game when it comes to the adoption of this AI, it also it also benefited the process. Because when we were talking about how to design the blades or the sort of constraints to put on it, they could chime in with, oh, hold on a second, you've got to put this limit on it. You can't make it any thinner than this, or you can't have it any taller than this. What material are we using? And can you program that in? And all these really insightful questions that the sort of the C-suite people probably wouldn't have thought of. So my suggestion for really getting the shop floor workers ready is to involve them in the acquisition and implementation process. They'll feel ownership, they'll understand it better, they'll be less scared of it. And when it's implemented, they'll take pride in the fact that it's being implemented rather than feeling that something's been taken away from them. That's my very strong advice.
Yeah, thank you. We've got quite a few questions, so I'll come to those momentarily. Before we jump there, and I'll come to you, Alexandra, first with this, but as a last question, what one piece of advice would you give the UK government in addressing decarbonisation for the manufacturing sector?
Oh, okay. Let me have a think. Can you, maybe I'll come back to this, okay? Because it's a very important question, I think. So give me a minute to think.
I'm happy to jump in there if you. I think from my experience, there is support in the industry from the government for industry, particularly through things like Made Smarter, for capital projects, so that typically steer away from software projects, and really everything that we're talking about with AI and data is largely a software project. So there isn't a huge amount of support for manufacturers to be able to gain grants to be able to pilot some of these things. Also, many manufacturers that we speak to, I mean, they're still running off Excel, and they're just not aware of what's possible. So I think a lot more education around what simple steps manufacturers could take that are cheap, low risk steps towards digitization will then get people started on that journey towards AI. As I keep saying, it's a critical prerequisite for AI to be able to have good, high quality data. Particularly in manufacturing processes. So I think the more we could educate manufacturers about things like simple sensors or lightweight MES systems or whatever, to be able to start capturing that data, deliver benefit early on at very low cost and risk, but then get them on that trajectory towards AI, I think that would be a huge thing that the government would be able to help support with.
Brilliant. Thank you, Craig. Alexandra, I'll come back to you.
Yeah, so I mean, I guess there are two hats here. One as a manufacturer. You know, in the UK, I think the latest statistic was that we have about 80%, 90% of UK manufacturers are SMEs. So, you know, as Craig was just saying, there is they don't have time, they don't have data, they don't have infrastructure. So I think the UK government can, and they are doing this, but a lot more can be done to done in terms of skills improvement, but also in terms of funding. You know, funding digitization projects in manufacturing, and creating really you know, a more coordinated effort that will help digitization. I think first digitization has to happen, and then AI can happen, right? Or you know, sometimes AI isn't needed. Sometimes it's, you know, as what Kit was saying, make the most of what you have. It needs to be digital. That's the first requirement, right? So sometimes simple statistics can work. And I think, you know, once that SME question isn't tackled, until that SME question isn't tackled, then, you know, supply chain questions really can't be tackled, because any OEM is dependent on their supply chain. So yes, and in terms of kind of the supply chain side of things, the government is already kind of doing quite a bit through their global supply chain intelligence program. Department for Business and Trade, in kind of trying to understand our dependencies, and that's kind of the first step. It needs to continue and scale up. Yeah. So those are my answers.
Brilliant. Thank you so much, Alexandra. And Kit, same question to you.
Yeah. So I'll preface this by saying, if there is anyone from the government that's listening, I'm aware that they are already attempting to address these things, but perhaps it just needs more. So I think what I've seen because I'm simultaneously on almost all sides of this problem, and what I found is that the potential adopters are there. There are more than enough companies who want to adopt AI for sustainability. The solution providers are there. There are an enormous of startups, more established companies with solutions to help companies become greener and to decarbonize. The two things that are missing are the connections, are ways for these companies, for the sort of the solution providers to find the adopters, and the money. Is that as Craig, I think it was, says, you know, most of the UK industrial sector is a bunch of SMEs, and they simply don't have the funds to try what they might see as pie in the sky new ideas. Even if the ROI is huge, if the I is too much, then they're still not going to be able to get the return. So I think more opportunities to connect the solution providers to the adopters, and more funds to help these connections form and do meaningful pilot projects, so that then once the return on investment starts flowing, they can become self-sustaining. It's that initial barrier, that initial kind of activation energy, as I'd say, as a chemical engineer, that needs to be removed. Because once that's there, it becomes self-sustaining, it becomes profit creating, and it will go, but you've got to get over that initial barrier.
Some great advice from all three panelists there on how we can accelerate the adoption of AI to solve some of these grand challenges. And we've got a couple of questions from the audience that I want to address before we all break. So Kit, I'll come to you first. And this question talks about, it's interesting to play with the operational parameters of any equipment, but how do you go up to a systems level? Can you connect process optimization with system analysis?
Yeah, so I'm acutely aware we've got short time here, so I will rattle through these answers. But if you do have any further questions, feel free to drop me an email. I'm eminently easy to Google. So it's a brilliant question first. It's a really, really good question. The crucial thing is the software that we have developed is extremely flexible. So the example I showed was coupled to a CFD engine, for example. But if you wanted to do systems level optimization, you can equally attach that to any other piece of sort of flow sheeting software, for instance, and you can actually optimize at the system level. If you have a very, very powerful supercomputer, you could actually do multi-scale optimization. So you could actually have an optimization engine attached to each of the individual processes, but also to the overarching systems level model. So eminently doable. The point of the software we created, you can clip it on to any piece of software that models either a process or a system. So it's just a case of designing the right set of constraints and the right set of objective functions for that specific model. Brilliant question.
Right. And one more for you, Kit, here. With the example you've showcased, does the system also take into account how long it may take to make new blades, materials, stress testing, as a consideration for what could be better options?
Again, excellent question. And I'm so glad that everyone's managed to grasp this concept so well from a very, very short introduction. So the answer is, you can program in any objective function, so any goal, any manufacturing goal that you like. So for instance, you can program it to have one of the objectives being manufacturability. You can make sure that it's actually easy to create, or some companies want it to be easy to clean. So you can put as an objective function, we want as few intersecting parts as possible. So absolutely, if you have a piece of software, for instance, that can predict how long it will take to manufacture. So the software creates a CAD file. Then let's say that you're 3D printing, we could add a bit of structure to the software. So from the CAD file, it then creates a G-code file, estimates how long it's going to take to print that, and then put that back into the objective function to say, right, if it's too long, we penalize that particular solution and might go for something else that's scored slightly lower in, say, the mixing rate or the grinding strength or whatever, but slightly better in the printability, in the printing time. Stress testing, again, instead of turning it into G-code, you take the CAD file, you put that into a finite element method piece of code, you do the stress test, then you feed that information into the optimizer as well. So yes, I mean, these are really great, interesting things to try, and you absolutely can. Anything you can code up, you can use as a goal, you can use as an objective function.
Yeah, that's a great place to end there. And I'd like to thank all three panelists for joining us today and for sharing some of the work they're doing. All three of you, I think, would be happy to be contacted via LinkedIn. Would that be the best way for people to reach out to you? Brilliant. Thank you so much. So just before you go and leave the webinar today, I'd like to tell you how else you can be involved with the ADViCE program. And so there is a number of activities that are coming up early next year. So firstly, our data science study group, and this is an intensive collaborative hackathon. In this case, we'll be looking at understanding heat pump performance. There will be opportunities for all of you to get involved. You can see a get involved QR code at the bottom there, or you can visit the ADViCE website. There'll be an upcoming webinar in January, hosted by the Energy Systems Catapult, one of our project partners, looking at enabling net zero infrastructure. And we also have our data science sharing circles. So these are small groups that meet for about an hour a month to share knowledge, best practice, establish working level relationships, and really get together and discuss how AI is being used, what are the challenges that you're facing, and to start to build that community of different players from the academia, from industry, from the innovation community, to look at how do we actually start pushing forward to net zero using artificial intelligence. So as I said, there are a number of ways that you can get involved with ADViCE. We are particularly interested in hearing from companies that are looking to decarbonize their industry through AI, companies that are looking at building manufacturing solutions for decarbonization, or actors in the decarbonization space looking to engage with others. And so the best ways to get in touch with us are to join our discussion forum on the ADViCE website, register your interest, and sign up for the next ADViCE webinar. You can see here just a few QR codes to get involved, and